Yay!
Yay! One really important example is the magnetic field from a straight line current, a segment of a wire or something. It turns out to be really, really important because we encounter that all the time. So suppose I have a current I, length L, the segment is length L, and up here, I want to figure out the magnetic field up there at some point. Let's say it's y away from the wire. So what we have to do is, let's see, we had this. B was mu naught over 4 pi, and then I had my, if it was just a point charge, I had my q over, let's see, I'll write it this way, r cubed, and then I was going to have a v cross r vector like that. I could write like that. I had this. I don't have a point charge anymore, but what we can do is look at this term QV. Even in terms of units, you can kind of, it kind of makes sense. QV, what is that? That's like a coulombs times meters per second, right? Well, what if I slide that seconds underneath the coulombs instead of the meters so that the product has the same units? So that would be like coulombs per second times meters. So what's coulombs per second? That's I. That's an ampere, right? And then the meter is the length. So it turns out that I can write this. Over 4 pi, and this is going to be I over r cubed, and this is going to be L cross r. So I can just replace the product QV with IL. And this is another form of the Biot-Savart law, this one for currents. So if I want to figure out what the magnetic field is, what I do is I chop that line up into lots of little bits dl with current I, and then I integrate them to find B. So now I got to integrate the Biot-Savart law. Okay, let's see. So this is going to be, let's bring the constants out front. Mu naught over 4 pi, I got an I. I'm going to integrate across the line. That value x is going to be 0 in the middle, right? So the limits are going to be minus L over 2 to plus L over 2. And I'm going to have just a little bit of length, dl, cross r vector over the distance from that little bit up to the point, that's my little r, all right, cubed. Okay. What makes me nervous is, okay, well, first of all, that r, that's just the, r is just the square root of x squared plus y squared, right? So I'll replace that in the denominator. That's okay. But that thing in the numerator, the dl cross r, that makes me a little nervous. What am I going to do about the cross product? Well, let's use symmetry. It turns out that's going to be really valuable. Let's just write down what that is. All right, so dl cross r. Okay, this bit up there, what is dl vector? Well, it's only got a component in the way that I've drawn it, just in the x direction, right? The current is just going, the segment is oriented in the x direction. So dl vector is just dl 0, 0. Here we go. From that little point, what is the r vector? How do I get from that little dl up to the point I'm interested in? Well, I go x, and then I go y in the y direction. I don't do anything in the z. So there's my r vector. So if I take this cross product between the two, okay, what's the cross product? Okay, again, I'll go faster. Again, what I do is I just take a little x, y, z. I just go around the cycle. So the cross product of two vectors, a and b, let's see, if I want the x component, I just go around the circle, a, y, b, z minus, and then I flip it, a, z, b, y. The y component is a, z, bx, then I flip it, ax, bz, and then z component is ax, by minus ay, bx. Okay, there we go. So if I take this cross product, look what happens. That first vector, anything with ay or az goes away. Boom, 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 boom. So those all go away. And then anything with the b vector, the second vector z component, that goes away. So boom, that's gone. So all I have left, look at this. All I have left is that z component, ax, by. So I just have a 0, 0, y, dl. That's what I get for the cross product. And what happens is, what if let's use symmetry. The only thing that changes is what if I get on the other side? What if I'm over here? If I'm over there, once I get to the other side of 0, then to get from that point up to the point I'm interested in, what changes? The thing that changes is that my x is going to be flipped around. So this is going to change to minus x, right, to get up to that point. But that's not even involved in the cross product, so it doesn't really matter. So if you keep evaluating that cross product, you're always going to get the same thing, which is just y dl. And that tells you that the magnetic field is going to have a z component. It's going to be in the z direction. In this case, it'll be out of the page, right? I've only drawn it in two dimensions. And then the magnitude is constant, y dl. So I can bring that outside of the integral, the y anyway. That's nice. Okay, so here's what this means. My b is going to be mu naught I y over 4 pi minus L over 2 to plus L over 2. And then what have I got? I got dl. And my dl is just going to be my dx. X squared plus y squared to the 3/2 when I cube it. We've seen this integral already. We've done this back in the electric field units. We've seen this one to death. We just look it up, or you might even remember what it is. So this is going to be mu naught I y over 4 pi. This integral is going to be x over y squared, x squared plus y squared, and then I go from minus to plus. Okay. Let's see, the y cancels with one of those. When I put in plus L over 2, look at the numerator. The denominator isn't going to change when I put in a plus and a minus, right? Because I'm squaring that x. The numerator goes from plus L over 2, and then it'll be a minus L over 2, so that's an L. So here's what I get. Oh, and this is in the z hat direction. I guess I have to write that down. So b is mu naught I over 4 pi, and then I got, here I'm going to have an L over y, and then I'm going to have a y squared plus L squared over 4. I mean, this is it. There's the exact answer. There's the magnetic field from a current segment of length L carrying a current I if I'm y units away from it. That's the exact answer. What often happens, though, is we'll use an approximate formula because often the wire is much longer than our distance from it. So if, oh, and this is in the z hat direction. If y is a whole bunch less than L, so if we're close to the line, what happens? Let's look at that. We have, let's see, then the L squared term dominates, and so we get, let's just do the magnitude because I'll keep forgetting to write the z hat in there anyway. This is going to be mu naught I over 4 pi, and then I'm going to have an L over y. Inside the square root, the L squared term dominates, so that's just going to be the square root of L squared over 4, so that's just going to be L over 2. So y times L over 2, the L's cancel. And what you have is the 2 comes up top, so it's just going to be cancels with the 4. So mu naught I over 2 pi y, where y is just the distance away from the wire. That's going to be really, really useful for us. So if you're close to, and what's the rule of thumb is like 10%. So if you're 1 centimeter away from a 10 centimeter long wire, this is a pretty good approximation. So if it's carrying a current I, You plug the numbers in, you see what the magnetic field is. I mean, just for kicks, let's keep the numbers simple. What about in like a laboratory? Is this something you could even detect? Suppose if I is, let's just keep the numbers easy, 1 amp. That makes it easy. And Y is 1 centimeter. So if I'm 1 centimeter away from the wire, what is a magnetic field of a wire carrying 1 amp if you're 1 centimeter away? Well, let's see. Mu naught over 4 pi, that's 10 to the minus 7, right? We got 2 of those. So this is going to be, B is 2 times 10 to the minus 7th divided by Y is 10 to the minus 2, 1 centimeter. So that's 2 times 10 to the minus 5th Tesla. Is that something you can detect? Sure it is, because it turns out this is roughly equal to the magnetic field of the Earth. So if you have a compass, for example, this is one of Faraday's early experiments. One of the first things he noticed is if you put a compass or some little magnet, something that measures the magnetic field, compass. I'll just say compass. If you put a little compass next to a wire and a 1 amp current goes through the wire, something you might find in an everyday lab, what happens is that the compass needle, this is one of the examples we'll do, the compass needle is going to jump if you apply the current. And this was noticed by people, that when you have currents that makes magnets, it makes compasses jump by some mysterious force, right? And then they call this the magnetic force. So there's a close coupling between currents and magnetic fields, because currents generate magnetic fields. And this was, by the way, how they discovered the Biot-Savart Law in the first place, was by moving the compass a little bit further away and noticing that it doesn't get deflected quite as much the further away you go. Okay, very, very neat.